As our third example, we now turn to the dynamics of a spin. Here we can give an explicit expression for the most general case of an arbitrary stationary Hamiltonian with arbitrary initial conditions. We will first formulate this solution in terms of the time evolution operator, and then describe the resulting wave functions for an explicit illustrative example. This problem can be solved exactly because the most general stationary Hamiltonian is a sum of the Pauli matrices and the identity matrix, with just 4 real coefficients. The term in front of the identity matrix can be set to 0, as it only gives an overall factor in front of the wave function, and we have seen many times that such a factor does not carry any physical significance. The terms in front of the Pauli matrices can be interpreted as a vector in space, which I denote as A, and then this part looks like a dot product, which is a convenient shorthand notation. In principle, we can make our life very easy here, and we will indeed do so initially. We can realign our coordinate system so that the direction of A simply becomes the z-axis. So let us look at this case as our simplest example. Then the stationary states are just spin up and spin down with energies of plus or minus az. Using our general expression from the superposition principle, the time evolution operator takes an exceedingly simple form given here. To keep expressions compact and facilitate their interpretation, I introduce here an angular frequency omega. The resulting dynamics has the simple interpretation of a rotation of the spin in space. We see this when we make use of the polarization vector, hence the vector of expectation values of the Pauli matrices that we defined when we introduced spin. For convenience, I here write it as a column vector. Let's say we determined this polarization vector at the time of the initial condition and then again at a later time t. We can relate the two directly by using the time evolution operator. And when we then transfer this operator into the inside of the scalar product, we see that this gives us a product of 2 by 2 matrices. And as any such 2 by 2 matrix, the result can then be re-expressed as a sum of such Pauli matrices. Note that we could interpret this as a time-dependent operator, and we will indeed return to this interpretation in the next chapter. Here we just use this to work out what this entails for the expectation values in the polarization vector. We start with the x component, which transforms as shown here. Using the Euler identity, this expression can be written as a sum of the Pauli x and y matrices. And when we reinsert this into the expectation value, we find the modified x component of the polarization vector. Here, omega appears in a very natural way, already suggesting its interpretation as the angular frequency of the rotation. And this is indeed confirmed when we look at the other two components. For the Pauli y matrix, we find again that it transforms into a combination of Pauli x and y matrices, and this then gives a corresponding expression for the y component of the polarization vector. The Pauli z matrix remains unchanged, and so does then the corresponding component of the polarization vector. We can collect these results into a single expression involving a standard rotation matrix in 3 dimensions. And what we conclude from this is that the polarization vector is then simply rotated, indeed by an angle omega t, about the z-axis. This rotational motion of a spin with a stationary Hamiltonian is known as Larmor precession, and the angular frequency is known as the Larmor frequency. It occurs, for instance, when a spin is exposed to a constant magnetic field, which here happens to point into the z direction. So this is the simplest case, but fortunately it already captures the main effects. To verify this, let us consider the most general case, which we can describe with just a little bit of extra effort. For this, let us first rewrite the vector A in terms of its length multiplied by a unit vector. I denote this unit vector as n and write the length again in terms of an angular frequency omega. We can verify that reduced to the unit vector, the combination of Pauli matrices here, that I denote as sigma z prime, squares to the identity matrix. This we can then use to evaluate the time evolution operator using its definition as a power series. What we see is that this series now alternates, with the even powers all proportional to the identity matrix and the odd powers all proportional to sigma z prime. So we can pull these matrices out, and what remains are ordinary power series just involving numbers, which happen to coincide with the definition of the cosine and the sine function. So we find a very explicit expression of this time evolution operator, directly written as a sum of the Pauli matrices and the identity matrix. And when one now again inspects the expectation values, one finds that this now corresponds to a Larmor precession with angular frequency omega, but about the axis n. In particular, when we work out the expectation value of sigma z prime, then we find that this does not change, verifying that this combination of components aligns with the rotation axis. This also follows from the fact that the time evolution operator only involves this combination of Pauli matrices. And in the derivation of this explicit expression, all that really mattered is that sigma z prime squares to the identity matrix, just is the case for any of the individual Pauli matrices. So what we are really doing here is just to use the Pauli matrices in a suitably rotated coordinate system. The corresponding Larmor frequency then follows when one considers the rotation of any other vector, for instance a vector that is perpendicular to the rotation axis. This frequency then turns out to be related to the length of the vector A in a natural extension of the expression that we obtained when it was aligned with the z-axis. Incidentally, this method to represent rotations in a three-dimensional space by acting on Pauli matrices is frequently employed in computer graphics. There one utilizes that these matrices replicate the algebraic properties of so-called quaternions. Okay, so far we looked at the most simplest and the most general case, and in both instances used the time evolution operator. So let us turn to an instructive case in between, and instead use the construction based on the superposition principle. For this we choose to align the vector A and hence also the rotation axis with the x direction. So this corresponds to a Hamiltonian of the following form. This would represent a spin with a magnetic field pointing in the x direction, but it also occurs in other contexts. Often what one considers are quantum systems in which there are two states that are initially treated separately, but then one looks what happens when one couples them together. This could, for instance, apply to an electron in a so-called double quantum dot. The electron can sit in the right dot or in the left dot, but due to tunneling it can also move from one dot to the other. And in this context, this parameter here, capital delta, is known as the tunnel splitting. So depending on the context, the two states of the system could be spin up and spin down, or they could be the left or the right state of this double dot system. But for concreteness, I will remain with the familiar notation that we know from spin. Irrespective of the physical context, the stationary eigenstates are the eigenstates of the Pauli X matrix, which we denoted as plus and minus, and correspond to the given column vectors here. The factors that we have in front of the coupling constant delta in the Hamiltonian transfer to the corresponding eigenenergies. They are included by convention, as in many problems the symmetric state tends to have the lower energy, and the factor 1/2 makes sure that the spacing of the two energy levels is just delta. Now, using the superposition principle, we can write the most general solution as a sum of just two terms, each corresponding to the time-dependent variant of these stationary solutions. Let us assume that the initial state at time t equal to 0 is just the first basis state. So spin up, or perhaps the electron in the left dot. This fixes both coefficients to 1 over square root of 2, and so the solution takes a very simple form, where one amplitude is a cosine and the other is a sine. First, we note that this remains normalized for all times. Next, we find that the probability for the two basis states oscillates, and indeed with the Larmor frequency given by omega equals to delta divided by h bar. So this is an oscillation of the probability for spin up or spin down, or for the electron being in the left or in the right dot. And finally, when we look again at the expectation values of the polarization vector, this clearly corresponds to a rotation about the x-axis, with the angular frequency again given by the Larmor frequency. In this example, this frequency once more looks very much like the Planck rule, and again this is applied to an energy difference, so a pattern seems to be emerging. And indeed, this pattern will solidify further when we make our next step and admit the Hamiltonian to be time-dependent. This will then allow us to consider transitions between these energy levels. Many other observations from the present chapter will be very useful for this setting too, including the concept of a time evolution operator and how we applied it directly to operators to obtain information about how expectation values change over time, as we did above to determine the rotation of the spin in space. Let us therefore move on to the next chapter.